Welcome to the office. I want to take a look at another theorem with you guys for cyclic groups here. And this theorem is maybe not the funnest to read through. So rather than providing a proof for the theorem, which again is available in the book, what I'd like to do is I'd like to just kind of walk through a particular group with you, trying to observe what this theorem is making, trying to make a statement of. So let's say we have G a cyclic group. Z12, for example, with n elements, 12 here, generated by A. So in Z12, generated by 1, right? So GB cyclic group, that this is, and we know that Z12, if we wanted to, 12 here, is generated by 1, right? Because it's a group under addition. So 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and so on. Let's see here, generated by A, excellent. And the size of Z12, how many elements it has, is exactly 12. Again, 0, 1, 2, 3, and so on, all the way up to 11, right? That stops at n minus 1 there. All right, so let B be an element of G, and B equal A to the S. Now, this notation for essentially all of the theorems, the notation assumes that we are representing the operation with multiplication. Now, that might not be the case, such as, again, Z12. So when we say, we can observe that 6 can be written as, let's see here, 1. Instead of to the 6th power, we would write it as multiplication, so 6 times, or the repeated addition, of course, right? 6 times 1. So, yep, the generator raised to the 6th power. Well, again, not multiplication, so we're using multiplication to represent the repeated addition. All right, so what do we have? Okay, we have Z12 generated by 1, 12 elements, fantastic. And we can pick something out and then talk about that it is this thing raised to that power, or this thing multiplied by that. All right, so that's what we're saying up to here. So we can talk about B generating a cyclic subgroup of H containing n divided by D elements. Okay, well, let's just take a look at what B generates. Let's look at 6. What does 6 generate? Well, 6 generates pretty simply here. It contains 6, of course, and then 6 plus 6 is 12. 12 mod 12 is 0, and then 0 plus 6 is, well, that's just 6 again. So it actually works out to be this subgroup with just 2 elements in it. Okay, so it created this cyclic subgroup, H. Fantastic. Now it's containing n divided by d elements, where d is the greatest common divisor of n and s. So in this case, we're saying, let's see here, n is equal to 12, because that's how many elements are in it. D, which is the greatest common divisor of n, which is 12, and s, which is this 6 here. Right, so s is equal to 6. That's what we're observing. 12 and 6, greatest common divisor there is 6. So we're looking at the size of the group generated by 6 should be 12 divided by d, which is 2. And we see that indeed that is the case. So the theorem states that it should be 2, and we observe that it is indeed 2. Excellent. Also, the generation of this set and that set, right, they're the same thing if and only if the greatest common divisor is the same. So it looks like 6 is the only generator of this group, because in order to have a greatest common divisor of 6, right, 6 would have to divide it, which means you can't have something smaller, and the only thing bigger is 12, which isn't in the set, okay, because 12 is 0. Excellent. So let's consider then, oh, see, I want to think about a way that this will work out. Okay, here we go. Here we go. 8. Let's consider what 8 generates. So just another example here. So 8 generates, of course, 8. Let's see, 8 plus 8 is 16. 16 mod 12 is 4. 4 plus 8 is 12. 12 mod 12 is 0. 0 plus 8 brings us back to 8. So 8 generates this particular subgroup. Again, n is equal to 12. D, the greatest common divisor of 12 and 8 is, right? This is actually 4. So we're saying that the group generated by 8, the subgroup that is, should have size 12 divided by 4, which is 3. 1, 2, 3 elements. Exactly, right? That's what we are observing there. Essentially, what it works out to be is how long does it take you to go through these things until you have a multiple of 12? So 8 times what, right? So if you think of the least common multiple, so another way to think of it, least common multiple between n and 8, right? The s, the power s here. So the group has order 12, and this particular thing is being raised to the s power, taking right, s is equal to 8. When are they going to have the same thing, the same output? And in this case, we'd have to run through 3 iterations. 8 times 3 is equal to 24, the least common multiple of 8 and 12. So you can recognize that that's what we're working through. If this is right, 1 to the 8th power, well, under this notation, 8 times 1, when am I going to get it to be a multiple of 12, bringing me back to 0? Okay, 3 times. But that's the same, right? 4 should be the same thing because well, let's see here. Maybe note the greatest common divisor of 8 and 12, we observed to be 4, which is also the greatest common divisor of 4 and 12. Now, so I wrote them as s comma n, but that's fine. So this is the case, and therefore we should expect 4 to generate the same subgroup. So 4 plus 4 is 8. 8 plus 4 is 12. 12 mod 12 is 0. Bringing us back to the beginning. Add 4, we get that. So indeed, it is the same. So we can see, we see that the group generated by 4 is the same group that's generated by 8. Excellent. So the question is now that we've made some observations here about how this theorem applies to a specific group. So you might ask yourself, what are the subgroups? What are the subgroups of Z12? Well, essentially, it works out to be what can you generate? Well, you can start at 0. 0, right? 0 is just 0. You don't get anything else out of that. So the subgroup generated by 0 is just 0. The subgroup generated by 1 is all of Z12. And now as we move, well, I guess not now, we'll get to repeated stuff here in a moment. As we move forward, when we look at the greatest common divisor, it should tell us that things are going to be the same. So 2 generates 2, 4, 6, 8, 12 gets us 0, and then it would bring us back to the beginning. All right, 3, right, still distinct from everything else so far. 3 generates 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, bringing us to 0. Fantastic. Notice here how many elements it should include. Greatest common divisor here is 1. So, oh wait, no. Sorry, greatest common divisor is 12. Everything divides 0, right? So we're good there. Greatest common divisor of 1 and 12 is 1. So 12 divided by 12 divided by 1, the greatest common divisor gives us the. Sorry, I'm looking at this piece right here. That's how many elements it has, and we did that computation here and here. So we know that greatest common divisor is 12 here. So 12 divided by 12 gives us 1 element. Greatest common divisor here between 12 and 1 is 1. So 12 divided by 1 gives us the 12 elements of Z12. Greatest common divisor is 2 here. So 12 divided by 6 is the I know what the answer is, and I keep saying what the answer is rather than the question. 12 divided by 2, the greatest common divisor is 6. 1, 2, 3, 4, 5. Uh-oh, 2, 4, 6, 8. Because I missed a 10 there. It's nice to check our work sometimes. And of course, 12 is 0 mod 12. There we go. So those are the 6 elements that we were expecting. The greatest common divisor between 3 and 12 is 3. 12 divided by 3 is 4. Those are the 4 elements. So 4 here, greatest common divisor is 4. So we're expecting to get the 3 elements that we found earlier, 0, 4, 8. And we have 5. Now, 5 is a prime number. Cool, that's really fun. In particular, 5 and 12 are relatively prime. So we know that, recognizing, right, this is 1 to the 0, or 1 times 0, or 0 times 1, 1 times 1, 2 times 1, 3 times 1, 4 times 1, 5 times 1. So what I'm focusing on here are the S values, not this particular thing, but the S value and how it is comparing to the number 12. So 5 and 12 are relatively prime, so their greatest common divisor is 1, so I'd expect it to have 12 elements, 12 divided by 1. And if we wanted to walk through the whole thing, we can do that. We start with 5, sure, then we go to 10, then we go to 15, which mod 12 is 3, plus 5 is 8, plus 5 is 13, mod 12 is 1. And of course, once we see 1, another generator, or a generator, then we should have everything. But if we keep adding 5, 1 plus 5 is 6, 6 plus 5 is 11, 11 plus 5 is 16, which is 4 mod 12. 4 plus 5 is 9. 9 plus 5 is 14, which is 2 mod 12. 2 plus 5 is 7. 7 plus 5 is 12, which is 0. 0 plus 5 again gets us back to 5. So we do see that that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, and we know that that should be everything because this and that have the same greatest common divisor. So now when we look at 6, we saw earlier that that is 0 and 6. Now we move into essentially repeats. What's going to happen at this point? Well, let's continue working here. 7, the greatest common divisor between 7 and 12 is 1. So we know that this is the same thing as that, which is the same thing as that. Now when we get to 8, the greatest common divisor here is 4. So it's going to generate the same thing as 4. For 9, the greatest common divisor is 3. So it's going to generate the same thing as 3. For 10, the greatest common divisor is 5, so it's going to generate the same thing as 5. For 11, that's relatively prime to 12, so that is going to generate everything. Same thing as 1, 7, and 5. Excellent. So we find that it should be relatively easy for us to find the generators. In particular, if S is relatively prime to n, the size, then a to the s is also a generator for the whole group. All right, so now we can look at things that are subsets of one another, right? And what we can do here is we can sort of recognize when one power divides another, right? A cubed versus a to the 6th. 3 divides 6, so we would expect a to the 6th to contain all of the things that, we would expect a to the 3rd to contain all of the things that a to the 6th does, since a to the 6th would be an element of what's generated by a cubed. So for example, 2 divides 4, 2 divides 6, 2 divides 8, and 2 divides 10. So we would expect, let's see here. Ooh. Is it everything? 10. I want to make sure that I say things correctly. So we have a 10 here, but we don't have everything. Yep. Sorry, I'm working through, and I have the right ideas, but I'm making a slightly wrong connection here. 4, this is certainly a subset of that. That's no problem. For 6, we see that is a subset of this. And for 8, we see it as a subset of that. But for 10, it's relatively prime, so it generates everything. Right. Oh, yeah. Because we want to be cautious there. It has to have, yeah. Sorry, I'm thinking, and I'm not saying complete thoughts here. So yes, 2 divides 4, so 4 should be a subset. 2 divides 6, so what's generated by 6 should be a subset. But the key thing here is that it is also still maintains relatively, or it still maintains that it's not generating the whole thing. Whereas 5 and 10 generate the whole thing. 10 does not generate the whole thing. That's definitely not the case. 10 should actually be the same thing as 2. This is not good. I say it's not good because I said it was 5 earlier and you were listening to me, which is correct. I'm glad that you did that. Why is 10 not everything? Well, because it contains the factor of 2. 10 plus 10 is 20, which is 8. 8 plus 10 is 18, which is 6. 6 plus 10 is 16, which is 4. 4 plus 10 is 14, which is 2. 2 plus 10 is 12, which is 0. So this actually gives us the same thing as 2, not 5. So it's going to be a subset of or equal to the smallest of the common divisors. Oh, yeah. 5 is not a divisor, so it's the smallest common divisor. It'll be a subset of that. I apologize. So what am I saying here? 2 divides 4, so 4 is a subset. 2 divides 6, so 6 is a subset. 2 divides 8, so 8 is a subset. 2 divides 10, so 10 is a subset. Now it's actually the same thing, but we should recognize when that is the case. So it will be a subset versus the whole thing. Under what circumstances? Contains an additional factor, so it's a subset. Contains an additional factor, subset. Contains an additional factor, so it's the subset. 5 doesn't actually divide 12, right? Whereas the additional factor of 2 divides 12. The additional factor of 3 divides 12. There's only one additional factor of 2, so it's the same as that one, divides 12. No additional factors that divide 12. So there we're keeping it the same. That's why we have that subset relationship. All right. So what are all of our distinct subsets? Let's see if we can figure that out. So I'm going to generate a subset diagram. Z12 is generated by 1, or 11, or 7, or 5. From there, we end up with essentially a separation of subsets. So your largest subset is going to be this one, which contains 6 elements. Your next largest is going to be this one. So what's from here, what's generated by 2 is the same thing as what's generated by 10, because the greatest common divisor is 2 for both of those. Here we also have when the greatest common divisor is exactly 3. So that is also the case for 9. But that's not the case for 6, because 6 contains both the divisor of 2 and 3. And in particular, that greatest common divisor is 6. So this, however, right, 6 is a subset of both of those. So we see Z12 has these 2 subsets. Contained within those is that one. We also have the subset generated by 4, which is the same as the subset generated by 8. And let's see here, this actually doesn't contain any other ones. So we have 0 will go at the bottom. We already have everything. We have 2. So this will go at the bottom. We have this one. We have this one. We have this one. 0, 4, yep, so 4, 8. We have that one. We have that one. 5 is accounted for. 6 is accounted for. 7 is accounted for. 9 is accounted for. And 10 is accounted for. And 11 is accounted for. So the only thing that we have left is the trivial subset. So you take your this goes down to this, which you can either go down to that or down to that. This goes down to here, which would, and a subset of this would be that. And then finally you have what's generated by the identity, just that itself. So this is a subset diagram. You'll see another presentation of it in the book. So this is quite a long example. I apologize about the errors through discussing some of that in particular. Oh, where did that go? It was generated by 10 here. So subset diagram. This will be part of what you're looking for in one of your assignments as well. That just about wraps things up for us. I'll make a comment here. Actually, might as well just append that. If A is a generator, we have actually already said this. If A is a generator of a finite cyclic group, such as 1 in the example above, then the other generators are the elements where R and N are relatively prime. So 1 generates it, excuse me. And then we said that 5 and 12 are relatively prime, 7 and 12 are relatively prime, 11 and 12 are relatively prime. I think that was it. 1, 5, 7, 11 are all relatively prime to 12. So they all generate Z12. That's just what this is saying. All right, let's call that good. That should be the end of it for the section. So thank you for your time and attention. Have yourself a wonderful day.